Okay, let's talk about multivariable optimization. So this is where optimization really starts to get interesting. We've talked before about single variable optimization, and so that's the case when you're looking for the minimizer x of a unimodal function which just maps from the reals to the reals. So in other words, there's one number that I'm trying to find here. So my function just maps, is just a function that sits above the x-axis. And then we talked about various different conditions that we could place on f here, which gave us the different types of single variable optimizations. But it's pretty limiting to just look at functions which sit above the x-axis. And a lot of the time, as we're going to talk about in optimization, you actually have a huge number of variables that you want to find the minimizer for, as we'll talk about in just a sec. So what we really want to talk about here is multivariable convex optimization. Now that word convex is a really, really important one for us, and we're going to spend a lot of time about talking about what that word convex means. Let's set it to the side at the moment and just focus on this new problem, which says that let's find the minimizer x, where x is a vector now of a convex function which maps from Rn to the reals. So that convex function word is important, and we will talk a lot about it later. Ignore it for now, and just think about the fact that x is now a vector. That's the important thing for us. So we're going to look for minimizer functions where we have to find lots of different numbers. So why should you care about this? Well, it turns out you should care about this for a whole range of reasons. So this type of optimization comes up absolutely all over the place. So here's an applied math example. So OR stands for operations research here, a particular branch of applied mathematics. And here's a problem where you have, say, 4 different fixed locations of factories. So maybe you're Amazon, and you have some warehouses at A, B, C, and D, and you're trying to build 2 new distribution centres somewhere in the middle of the country, where you're going to distribute goods between these places, right? And you want to, you have to. It costs you money to drive materials along from A to X, or from B to X, or from X to Y to drive between all these places. So you want to build your 2 new warehouses, X and Y, in good locations such that you minimize the total travel time that you have between these different places. So you can move X and Y around. A, B, C, and D are fixed. But you want to minimize the amount of road that you have to cover. So the problem there is then to find where to put these new warehouses X and Y such that you minimize the total length of all of these blue lines. So what I've got, this cost function here, is the distance from A1, X1, and A2 to X2. So that's the difference from A to X. The next one is the distance from B to X. Then we have from C to Y. We have from D to Y, and we have the distance between X and Y are all the terms there. So that's a pretty ugly looking cost function, and I've got 4 things that I'm trying to find here. So X1, X2, Y1, and Y2. So that's a really important problem in applied math, and it's a multivariate convex optimization problem. So that's sort of classical applied mathematics. If you're Amazon, you care about solving that problem. There's something that's even more ubiquitous in the modern world than that, which is data science or statistics. Regression, so any form of statistical regression model is, or it can be cast as an optimization problem. So here is a sort of cost function for, I guess this is essentially the cost function for polynomial regression. So if yi and xi are a bunch of data points here, and if you're trying to fit some form of polynomial p to those data, to fit some sort of curve that fits through this data, that's essentially what you're doing in regression polynomial regression. And in fact, linear regression, the cost function for linear regression essentially takes, minimizes the sum of squares of the errors, the distance between each data point and the line. So you imagine that this p of xi is the equation of a straight line, right? So a constant plus a linear term, minimize the squared difference that you have between each data point and that line, and that's what you do in linear regression. Right, so that's linear regression for one variable. You can have linear regression in multiple variables, which means you chuck on extra terms here with with different x's in them. But that's how linear regression works. It actually minimizes that cost function. And you might say, well, I've done some stats. I know that you can write that down as a linear piece of linear algebra. You can write a design matrix down, and you can write this as a product of a few matrices with inverses. Actually, the dirty little secret of even linear regression is that once you get up to big data, once you have sort of tens of thousands of points here, you have quite a large sum here, which converts to quite a large design matrix. And particularly if you have lots of different variables, then actually doing the linear algebra version of this is really inefficient. And the way that you actually want to fit your linear regression model is by finding the minimizer of this cost function with respect to beta naught, beta 1, and however many parameters you have there. So it's actually more ubiquitous in regular statistics than you might think. It gets even more necessary, though. So for statistics people who have learnt about logistic regression, which is where you have data xi, but you're trying to predict some binary variable, you're trying to do some classification, so predict whether yi here is a 0 or a 1, then the cost function that you get for logistic regression, which this is, I've written down a log likelihood here for the people who know that. If you don't know the terminology, it doesn't matter. The cost function that you have to minimize for beta naught and beta 1 in the simplest form of logistic regression looks like that. And actually here, you have to use optimization. Because if you try to differentiate this and set it equal to 0, so you're differentiating with respect to the parameters there, beta naught and beta 1, and setting equal to 0, you can't solve that. That's called a transcendental equation. So there's no analytic solution. So straight away, whenever you want to fit logistic regression, so whenever you want to do classification at its most basic level in data science, you have to solve a multivariate convex optimization problem. So right there, if you've heard of logistic regression, optimization is getting done under the hood. It goes even further. So in the modern age, if we're going to talk about machine learning, so things that are at the forefront of machine learning, methods like deep learning here, these fundamentally rely on optimization. You can't do anything without optimization in these things. So this is a nice paper. I like it because it's an introduction for applied mathematicians, and as an applied mathematician, it's quite readable to me. And it sort of explains the mathematics of deep learning. So you should check this out. I'll give you a crash course right now. This little paper goes through how deep learning works for a classification problem like this. So let's say you've got two variables here along the x and the y axis for something that you're trying to classify. Let's say that each of these points in here represent dogs and cats. Maybe the red circles are cats and the crosses are dogs, and you're measuring, I don't know, pointiness of ears or something, and some measure of the shape of the face or something here. And you're trying to come up with some surface that clusters those blue X's together, that separates out the dogs and the cats from this. And you want to be a fancy pants machine learning person, so you write down a deep neural network, where the idea is that you've got two coordinates here, so x and y, which you feed into this so-called input layer, and then that goes through these fancy neurons, and it outputs dog or cat over here at the other end. Now, that's an inscrutable diagram. What's actually going on, what's happening in each of these black dots here, is the data is getting fed through a sigmoid function. So a sigmoid function is something that looks like this. You're taking the value of x and the value of y in that little picture, and you're feeding it through these functions that look like this. And actually, what I'm composing is some weights here. So my data are these AJs here, I believe, and we're looking for some weights to shove into those. So I need to figure out, what values each of these parameters should take. And then actually what we're doing, so when we actually feed data into a neural network in this sort of configuration, what I'm actually doing is I'm taking the data and I'm composing it into a sigmoid function again, and a sigmoid function again. So there's my input layer, and I compose that, feed that through this sigmoid function. Then I do it again. I shove that into another sigmoid function, and I shove that into another sigmoid function. Right? And I come out with two numbers at the end which tell me dog or cat, essentially. And the things that I'm looking for, the things that I need to solve for, are these W's and these B's in this, where sigma is this funny nonlinear sigmoidal function. So what one does is one writes down a cost function again. So I have data, so my y of xi's here inside this cost function. That's a binary indicator to tell me whether my image is a dog or a cat. That's a 1 or a 0. And then I have data that I feed in, which is my x and y coordinates from my little picture before. I feed it through this very complicated, ugly function here, right? And then I get some crazy sum. So this looks like a least squares, a sum of squares here, squared errors, sort of like in the regression frameworks. And then depending on what W2, W3, W4, B2, B3, B4 are, those vectors, then that gives me some cost function. I'm trying to optimize that. So this is now a very high dimensional already multivariate optimization problem. And to actually fit my neural network to be able to do this prediction, I need to find the minimizer of that cost function. And that's how it works. So this is, so if you actually do that optimization, the thing works, you actually get a surface out that looks like this. So optimization, particularly this multivariate optimization, is genuinely used all over the place. So deep learning doesn't exist without optimization, because I've got, hopefully you can see this is an ugly cost function here to optimize. And even things like traditional stats, linear and logistic regression, don't exist without optimization. So this is a very, very important topic. It will occupy us for the rest of the course, actually. And we're going to get into it very soon. That's it.